Greetings and welcome to another installment of Quant Slob. This is fifth in our basic application series. This time around, part 4 in our mini-series on probability sampling distributions. We're going to do a quick inventory here. Starting with our population comprising the 52 cards in a standard deck of playing cards, we looked at the sampling distribution of the sample statistic here, our proportion of cards suited as clubs in our theoretical sample. As a reminder, we specified that the theoretical samples had to contain unique cards, no duplicates in the sample. In our examination, we learned that at the limit, when we sampled the entire population, all 52 cards, the sampling distribution collapsed. So to say, the probability that 1/4 of our sample is suited as clubs is 1. No other proportions are possible here. And just as an FYI, probability distributions where one value, be it a quantity or a category, occur with probability 1 are sometimes called degenerate. Degenerate, like your little nephew that keeps putting the remote control in the fish tank. Again, with our standard deck of playing cards, we constructed an attribute, integer rank value of card. And we ran our animation up to a sample size of 26, and we saw this as the resulting sampling distribution of the average integer rank. We didn't show it in the previous edition, but had we sampled all the cards, our sampling distribution would be degenerate at 8. The population average, and I'm hoping that this is not a surprise to anyone at this point. We lastly looked at the sampling distribution of the proportion of heads in an imaginary infinite population comprised of every possible toss of a coin. And at a theoretical sample size of 500 flips, we arrived here at this probability sampling distribution. For this edition, we're going to look at another example. We're going to consider the infinite imaginary population of every possible spin and ball landing of a European roulette wheel. And we're focused on two related attributes, whether or not the ball lands on ought or green 0 and the net winnings on a $1 straight wager on green 0. Here is the distribution in table form of the net winnings attribute in our population distribution. We're going to create a sample statistic, the average net winnings, and here's the distribution of our average winnings in a theoretical random sample of size 1. The probability that we're going to lose $1 is 36 over 37. The probability that we'll pocket $35 is 1 over 37. And once again, RV stands for random variable here. Showing the previous table graphically, like we are here, brings something important to light. We have this huge mass. You can see it a probability at negative $1. And we've got this little blip of probability way out here at $35. In fact, it's at a short glance, it's barely visible in the graph, so I got this red circle here to sort of draw attention to it. We might describe this distribution as lopsided or skewed, as in skewed to the right. So what do we do next on QuantSlob? Well, we animate, of course. We're going to see how the probability sampling distribution of our sample statistic average net winnings changes as the sample size grows. And we're going to do this by looking at a sequence of 5 short animations. In all 5, we're going to be zooming in here. You can see it on the x-axis, just like we did with the coin tosses in the previous edition in this mini-series. This first animation, our sample size counter rolls us forward from 1 to 100. And here we are, sample size of 100, sort of bell-shaped, but clearly lopsided or skewed. So in a sense, we see that even at a sample size of 100, this sampling distribution has inherited, so to say, some of the skewness we saw in the original parent distribution. So now we're going to roll forward from 100 to 1,000, but here by increments of 10, just to speed things up, keep things moving forward. And we arrive here at a sample size of 1,000. And if you're very sharp visually, if you're a very good visual person, you'll be able to detect that even here, at a sample size of 1,000, this distribution is very, very slightly skewed, but it's very subtle. We're going to roll, keep going here. We're going to roll up to a sample size of 10,000, this time by increments of 100. At a sample size of 10,000 here, now we've got what appears to be a pretty symmetric and nicely bell-shaped distribution, at least visually as far as we can tell from the graph, very much like we saw with the coin flips in the previous edition. And we're going to keep going here. We're going to keep rolling forward. Here our counter is going to roll us forward by increments of 1,000 all the way up to 100,000. And we arrive at a sample size of 100,000, very nicely symmetric, bell-shaped. So one more. We're going to roll all the way up by increments of 10,000 to a theoretical sample size of 1 million. 1 million. Theoretical sample size of 1 million. So here at a sample size of 1 million, very nicely bell-shaped, at least as far as my visual acuity can tell from the graph. We've zoomed way in on our x-axis here, by the way. The width of our x-axis when we started was like $60. Here, it's maybe 6 cents, the span of the x-axis. $60 is 1,000 times more than 6 cents. And this actually means something. One last thing. Notice how crowded our domain of values has become. In fact, just in this very small region on this graph, this sample statistic can take on about 1,400 values, about, give or take. In other words, even though they're difficult to see in this plot, there are about 1,400 purple vertical lines here defining the mass of this distribution. And that's it. That's going to do it this time around. Thank you very much for tuning in. Always dearly appreciated. And don't forget to stay tuned for more Quant Slob.